So in evaluating limits 1 through 6, all of the limits have x either approaching positive or negative infinity. That puts us in this category of what I like to refer to figuring out these limits using the bubble theorem. Now the bubble theorem, the idea is a concept. It's not an actual theorem, but the concept is if the denominator is going to grow significantly faster than the numerator, then the limit would be 0, because as the denominator gets a lot bigger than the numerator, then the fraction's value continues to get smaller and smaller. And then in absolute value, it could get smaller or closer and closer to 0 from the negative side or the positive side. Either way, the value of the fraction is tending towards 0 if the denominator continues to get bigger and bigger. And then if the numerator and denominator basically grow at the same rate, then we would just peel off the coefficients of the leading terms and we would have our limit. And we'll get to that in a couple examples here. And then finally, if the numerator of the fraction is growing significantly faster than the denominator of the fraction, then the value of the fraction keeps getting bigger and bigger and bigger. And again, when I say bigger and bigger, I mean it's either bigger in the positive direction, so towards positive infinity, or bigger in the negative direction, which would mean that the limit would be negative infinity. So how do we apply that to, let's say, problem number 1? Problem number 1, we have a very straightforward limit because we notice that x is approaching infinity, and therefore the numerator has a degree of 1, the denominator has a degree of 1. That would mean that the bubbles are the same size, and this limit then would be equal to the leading coefficients, the ratio of the leading coefficients. So 4 divided by 2, and that's 2. Now, what could you do? You could analytically, if you wanted to think about this a different way and show all of the steps analytically or algebraically, we could multiply top and bottom by 1 over x. I would not suggest doing this, but this is algebraically how you would do this. If you distribute 1 over x to both terms, you get 4 plus 3 over x in the numerator. And if you distributed 1 over x to the denominator, you'd get 2 minus 1 over x. Now, then when you replace x with infinity, 3 divided by infinity, that goes towards 0. And 1 divided by infinity, that also goes towards 0. And you get 4 divided by 2. And again, we get a limit of 2. So like we talked about the what, or the concept of the leading coefficients, if the numerator and denominator have the same degree, being what drives the value of the fraction. And I mean, again, conceptually though, if you think about it, if you take, let's just say 10 billion, 4 times 10 billion plus 3 divided by 2 times 10 billion minus 1, the 2 times 10 billion minus 1 is really close to 2 times 10 billion, or 20 billion. And the 4 times 10 billion plus 3 is really, really close to 40 billion. So 40 billion plus 3. So really the plus 3 and the minus 1, those are insignificant. And because they're insignificant as x approaches infinity, we can act as if they're not there, because what acting as if they're not there does is it gives us the value of where this fraction is going, or the y-coordinate that this fraction is heading towards. And you might remember when we were analyzing rational functions, we would say y equals 2 then would be a horizontal asymptote. We would say a horizontal asymptote is y equals 2. So we've already studied the concept of limits without calling them limits while we were analyzing rational functions. And let's see, what else do I want to say about that? That's a lot of instruction on one problem, and I will not take that much instruction on the other problems, but I wanted to make sure that you got the concept of what we do and what it means when x is approaching either positive or negative infinity. All right, so I'll stop this video here.